my name is Pawan, and you're going to see some of the strategies in terms of architecting your serverless applications. When I talk about serverless, these are AWS serverless services. How can you achieve that hyperscale? I've been based out of London, UK, working as a principal serverless specialist at AWS Amazon. I'm also an author at Pluralsight, which is an online course or education system. Cool. In terms of the agenda, the key takeaway is for you, at the end of the session, you will have those 8 best practices that you will learn in terms of how can you make your applications hyperscale, the serverless applications. We're going to take an architecture that's based off the real world use case. I'll tell what that is in a bit, and also some of the best practices and the toolings that you will see. Quick one, that we are not going to go into the basics of like what are the serverless, what is API gateway, what is Lambda and things like that. However, don't be disappointed in case if it is all new for you, there's always something to learn about it. If you want to learn about these services more in depth, there's also a QR code in some of these slides, so feel free to take the picture, which will take you directly to that to the site. So here we have the resources in case if you already you don't know anything about serverless and you want to get started, or you already have the specialization knowledge but you want to always keep learning and growing and upskilling. There's also those ramp up guides available. There's also the certification and the digital badge that you can also get that you can add to your online profile. All right, so in terms of the application today, so this application is inspired by the real customer application that was launched during the COVID-19, where the application had to scale literally to millions of users, right? So what does this application look like? So you have a front-end application that is hosted on S3, which is served via the CloudFront, which is the CDN here, content distribution network. And then for the dynamic side of things, you have the API gateway, which serves as an API endpoint, behind which you have a Lambda function where it holds the code for your business logic. And then the Lambda function talks to the database. In this case, it's Amazon Aurora, which is a relational database, as well as a NoSQL database, the DynamoDB. The application also has the messaging components here, where the application, once the operations are all complete, it sends a notification via the SNS to send out SMS messages, as well as email notifications saying a particular task is complete. So this is just a base architecture. So over the session duration, we are actually going to evolve this and improve it and make it virtually scale to any level. So you'll see some of those things here. So let's see the first one, which is the API gateway. So API gateway is a service which allows you to create, manage, deploy APIs at scale. So this is always available, a multi-tenant architecture, which what does always available here mean? So by default, when you are creating an AWS account and you want to deploy an API gateway, by default, you get up to 10,000 requests per second. And this number is by default, like, you can always increase it. It's an adjustable number. Now, as and when the request comes, your application or the API can scale instantly to that quota. So that number, whatever the number can be here. The few other quotas that come into play is API gateway can be integrated with your backend. This can be Lambda function, this can be step functions, or literally any other services. And the key thing that to keep in mind is there is integration timeout which comes into play. So that's roughly about 30 seconds, as well as a payload size, which is 10 MB. So these are the incoming requests into the API gateway to handle it. It includes a link, QR code here for other quotas as well. So that's API gateway. Let's take a look at AWS Lambda. So AWS Lambda, when it comes, there is a concept called as concurrency. So when a new request comes in, basically there's a way to invoke a Lambda function. There are 3 primary modes of it: synchronous, asynchronous, and then there is poll-based. So when this request comes into the Lambda function, it creates something called as an execution environment, which handles that request. Now with services such as Kinesis or SQS or DynamoDB streams, you have the ability to batch this request and still execute it as a single event. Now, whenever there is a new request that comes in, then if the current execution environment is already busy processing it, then it'll start spinning up more and more execution environments. So let's look at the flow or the life cycle of this function when you create these micro VMs, right? So it starts with downloading your code that you have written onto the execution environment, and then based upon your runtime that you have chosen, like it could be Python, it could be Java based, it could be Node.js. It also allows you to bring your own runtimes as well. So the runtime gets bootstrapped, and then finally it will start initializing your init code, which is the initialization logic. This is outside your handler code. Now, at that point, your function is ready to execute whatever the logic is inside the handler. So that's where the warm start starts taking place. And anything that you see has a full in this particular diagram is pretty much a cold start. We'll revisit this particular slide in a bit, but keep this thing in mind. Now, talking about the execution environment, so when a request is handled, that execution environment is kind of blocked for that entire duration while the execution is happening. Now you can see the blue part and the orange part. The blue part is basically the cold start that we spoke about, where your bootstrapping and the initialization that all starts happening. While your request 1 is executing, if there are more parallel requests that comes in at the same time, what the Lambda service will do is start spinning up more execution environments, right? So you have request 2 and request 3 that is executing. After some time, you have request 4 and request 5 that comes in. But if you notice the request 1, it's completed, right? So what does that mean is that environment, that execution environment is now ready to take more requests. So it's kind of warm for you. And if you see that it doesn't have the blue part in, which indicates that that execution environment is like fully warm, ready to handle multiple requests. The same thing happens for the other execution environments. The request 9, while all the other executions are busy, Lambda spins up a new execution environment to handle the requests. So where does concurrency fit in all this picture? So if you draw a vertical slice, and if you kind of count the intersection, that's basically nothing but your concurrency. So at the initial start, you can see there is 3, and there are 5 parallel requests that's executing, so you have 5. So in CloudWatch and AWS, you have a metric that you can actually see over the time scale that how much concurrency is going on for your execution or for your Lambda function. All right, coming to the important bit. So keep in mind, when it comes to Lambda scaling, there are 2 concurrency quotas, or the 2 scaling quotas that comes into play. The first one is called as account concurrency. So this is a maximum concurrency that would be allocated for your account per region. So every region you would get 1000 as your default Lambda limit. Now this is not the maximum number, but it's something that has a baseline, right? You can always open up a support case and ask for more if you need. The second concurrency, or the second quota that comes into play, is burst concurrency. And if you see that it's highlighted as new here, I'll tell you the reason why. So if you're familiar with the previous Lambda model, the way how it was scaling, so initially it will launch 3000 containers, and then you will have a stepped approach of 500. So that was a previous model. Now, as of last year in November, we actually made an improvement to that feature. So what's going to happen now is the way how the burst works is you get 1000 executions environment, the concurrency, every 10 seconds, and this is per function versus the previous model, which was applied to all your functions, right? So this is massively scalable, close to like 12x improvement. So how does it work like in practice? So just to show you like in a graphical way. So let's say I have an account here where the concurrency is already, I've opened up a support case and got the concurrency increased to 7000. And my application is receiving, is at a baseline 1000 concurrency. There are a few things going on, right? The next 10 seconds, at the 10 second, I receive 1000 more requests. Not a problem. Lambda service will spin up more 1000 concurrent execution environment. It will handle it fine. Now this keeps happening. So the next 20th second, there's 1000 more requests coming in, right? Now at the 30th second, you can see that instead of 1000, I've received 1500. Because the Lambda scaling only takes 1000. So what that means is the balance 500 will start throttling those requests. Now it's up to the client who's invoking these functions to retry those functions later on. So it depends on whether it is synchronous, asynchronous, and those requests will be retried. In this case, it was retried at the next 10th second, which is at the 40th second, and you can see that it has provisioned another 500 more. So it keeps going on. So you get the idea, it keeps going. The concurrency keeps adding. So what happened at the first minute here? So here, all of a sudden, you were having like 4500 execution environments, but I got a burst of 3000 requests. it still follows the same model of 1000 concurrence. It handles that, and the remaining 2000 will be throttled. And then retry, it works, it keeps going. So you can see that very quickly, within a span of a minute, it has gone from almost 1000 to 7000 concurrency. Now the last bit is a bit interesting, because you can see that the account concurrency is capped at 7000, right? So now I have 6500, which means that I'm left with only 500 concurrent requests left. But I received 1000 there. So what that means is 500 will be served, and the rest 500 will be throttled throughout. So if there are cases where you want to go beyond that, you can again open up a support case and request for more. So this is how the burst works, burst scaling. All right, there might be use cases where even though you can see that how fast these the Lambda scales here now with the new feature launch, there are some use cases where you might instantly need all the execution environments up and running. You had lunch today, so think of an app, a company who actually would order food, right, instantly, and they know that at 11 o'clock people are going to order food. So they need all the containers warm and ready at that time. So this is where a feature, something like feature called provision concurrency would come into picture, where for a specific function you can actually say what's the floor or the minimum number of concurrent executions that you would need for a function version or an alias. So what the service will do is behind the scene or ahead of time, it will warm those containers and keep it ready for execution. In certain cases where you have really good utilization, the numbers show that it is, if your utilization is above 60% in terms of provision concurrency, you can also, it can also be a way of cost effectiveness as well. So it becomes cheaper than the on-demand model. On the other hand, the flip side of this is the reserved concurrencies, right? Instead of the minimum, what if you want to have a cap, right? At any given point, my Lambda function should not go beyond this particular number. A use case might be saying that if your Lambda function is sending a message to an SMS system, which can only take 10 requests per second, and you don't want to overwhelm that system, downstream system, right? At this point, you can actually set a reserved concurrency on that function so that it doesn't go beyond that. All right. So let's look at the second practice, optimizing your Lambda function. So there's a way to calculate your Lambda concurrency, and the formula for that is if you know your requests per second that's coming into your Lambda function, and how long your executions are, which is nothing but your duration in seconds. If you multiply these two, you can kind of estimate what's a Lambda concurrency that you would need. Here are 3 examples. So 10,000 requests per second takes about 1 second to execution. You need 10,000 concurrencies. Again, 10,000 requests, but now the execution duration has dropped to 500 milliseconds. You need 5,000 concurrencies. The last one is it's dropped down to 100 milliseconds. You only need 1,000. So you kind of get an idea here, right? As your function execution time increases, you need less and less concurrency. So keep this in mind. The key takeaway here is longer your function executes, the more concurrency you would need. So here is an optimization opportunity that you can consider to see, can I make my function run faster? This one is a lesser known Quota, or it's documented in our public documentation, but we don't speak as much about this particular one. So each execution environment, there's another limit that comes into play of 10,000 requests per second. So if you have a function that is execution 100 milliseconds, and you get a steady state traffic of like 10 transactions per second, you're well within the concurrency limit. But what happens if you have a function which is 50 milliseconds, right, which goes super fast? What happens in this case? Like, do I get double the capacity or double the concurrency, right? So there's a math in our documentation which actually talks about this one. So let's say you have 3,000 requests per second, which is taking about 20 milliseconds of execution. So working by that example, you can see the concurrency roughly works out to be 60, right? But keep in mind, there is per execution environment, there is a limit of 10 requests per second, especially which comes into play when you have a sub 100 millisecond function. What that means is for 60 concurrent executions, you can only go 600 requests per second. So in order to serve the 3,000 requests per second, ideally in this case, you would need 300 execution environments. So something to keep in mind when, especially if you have functions which are executing like quite fast. All right, revisiting the function lifecycle again. So here there are two things that you can see in the screen, like one which talks about AWS optimization, and the other one is the optimization as a developer, as a customer you can do. Now, from an AWS standpoint, we are responsible for all the undifferentiated heavy lifting, making sure these execution environments are spun up as fast as possible. And over the period of time, we have done like a lot of improvements that has helped in this particular front. But what are some of the things that you can do on your Lambda function to optimize your function code? Are there things that you can improve to make the cold start go away? Now, first of all, do you have a cold start problem, right? How do you identify that? So we do have a query called for the log, using the CloudWatch log inside, that can kind of give you an idea that if you are having increased cold start, and what are the number of cold starts, right? So there is a link and the QR code here which will take you straight to that page. But this would be a good starting point to kind of see what is your average, perhaps even the 99th percentile and even the maximum, to try and see what are the things that you're doing outside the handler code and the initialization, why is it taking time, and improve that. Some of the optimization practices that in this particular front that you can actually do is like, we have seen it's a natural tendency where if you need a lot of libraries, you would load all the libraries at the start. Do you really need to do that? Can you use something like lazy loading techniques to load only these things? So that will massively help in the cold start. Again, minifying your code can massively reduce that deployment package size, which can scale your functions faster. There's also a feature called as snap start. This is available only for Java, but that can also massively improve your cold start. Now, this itself is a talk on its own. It's a 1-hour talk. So there's a link that I have included in this presentation, so which talks about much more optimization things that you can actually do when it comes to the cold start optimization. Anybody use Lambda Power Tools here? Okay, a few of you, yeah. So one of the things about Lambda is where if you have a function that is CPU intensive, it can the way to dial up your CPUs or allocate more CPU is by increasing the memory size, right? Now there's a manual way of doing it, like you have to do it manually and test it. But is there a methodological way to do that? Yes. So this is where the Lambda power tuning can kind of help you. So what this does is it's a single-click deploy solution that you can deploy it into your AWS account, and it will work through the different combinations of your memory of your Lambda functions, and then kind of to show you which is the best one. So let me show you a demo. So here I have a function. It's not super exciting. It just generates a few it generates prime numbers, about 100K prime numbers. Now I'm going to test this application. So let's take a look at the configuration. So you have 128 MB, which is the default memory that will be allocated to a function, right? So let's go ahead and test this function and have a look at a few things. So first you'll see, because it's a cold start, you will see the init duration flag there, or the variable there, and it's taken about 2 seconds for execution, right, for generating 100K prime numbers. Now, if I execute it one more time, that's your warm start, right? Your container is already warm and it's executing now as a warm start. So you can see that the init duration is gone, but still the execution duration is roughly about 2 seconds, right? Now, what if I change my memory on this particular function to 256, right? Because this is prime number generation, and it is known to be CPU bound. So let's do that and then run a test once again to see the behavior. Right? So the function has been deployed. Now, when you make a change to a function, it will always be a warm start. So this first execution will be a warm start. So you can see the init duration that will indicate that that's a warm start. But you can see the duration has dropped by 50%. So from 2 seconds, it's already dropped to 1 second. So it's 50% faster. So this is one of the way to test it. But now let's look at the step functions, or the AWS Lambda power tuning to see if there is an automated, or how do you do this in automatic way. There's also CI/CD solutions that's available that you can configure Lambda power tuning to automatically do that in your pre-production environment and then deploy it to your production once you complete this test. So for execution, it needs a few parameters. So in terms of what your Lambda function ARN looks like, what are the memory settings that you are interested in. So starting with 128 MB, 256, and keep adding a few things. You can also pass in the payload as well, number of iterations that you want to do the test on. Do you want all the invocations to happen parallelly, which is the default option here? And then you can use a strategy here, which is for cost optimization. So with these parameters, this is all documented very well here. With these parameters, let's execute the step function. So what this is doing behind the scene is spinning up multiple Lambda functions with all of those different memory sizes, and then performing the test. And then at the end of it, you'll see that it will consolidate the results and show you in a bit. And in the results section, you can see that it will kind of summarizes and shows you what is the actual optimal settings in this case. But what I love is it also gives you that visualization graph, which is super handy at times, like to kind of give you that visual picture, right? So if I open that graph here, you can see the two lines here. The orange line or the red line basically indicates your function execution for the memory size, as in when you dialed up, you can see that the performance has gone much more faster. And the blue line is basically the cost for execution. So somewhere at this point, basically, after that, the cost has gone up. So this kind of serves me or tells me that this is a sweet spot, and I can configure 1 gig as the most optimal settings for this particular Lambda function. So again, it varies for different functions, different Lambda functions. So recommend testing it thoroughly using the tool like this. All right, so let's take a look at the third best practice, right? Asynchronous. So wherever possible, asynchronous should be your default. So revisiting our architecture again, so we're going to look at the messaging bits of it, right? So what this Lambda function, so the request from API gateway goes into your dispatcher Lambda function, and then it goes to SNS, and then it goes makes another call to an SES. Some of the challenges with this kind of an approach is, you have your the entire flow is synchronous here, right? If there is a burst of traffic that comes, that could very well deplete your dispatcher Lambda function concurrency, which we don't want that to happen. And there's no concept of you can't do a batching in this case, which probably would help in situations like this. So what are some of the improvements that you can do in this particular architecture, in this particular case? So the first one that you can do is by adding a queue, where you can have the dispatcher functions send the messages into the queue, and then you can have the Lambda function batch those requests up and then read from the queue and then send it to the downstream system. So adding a queue is definitely a battle-tested pattern where you can actually follow the asynchronous model. Now, because initially I told that the downstream system in this case might not be able to handle the scale, right? So how do you actually take that into consideration? So this is where you can apply the reserved concurrency on your Lambda function, which reads those messages off the queue, right? In this case, it's set to 50, so that your downstream systems are not overwhelmed. And then obviously when you batch and read those messages from a cost standpoint, also it helps versus previously where you were reading one event at a time, right? But even though we have improved this architecture, it doesn't completely, there are some opportunities that's available that you can actually improve further on. So what are those, right? Here the dispatcher Lambda function, if you notice, it is still doing synchronously enqueuing those messages. And still you would have the problem of the concurrency burst depleting your account concurrency. So in this case, the Lambda function was just routing the request based upon a certain parameter. So one of the options that you can use is, instead of the Lambda function, you change it to event bridge and then configure a rule. The rule would probably match looking at the payload saying, okay, if there is an email field, then send it to the SQS. Otherwise, if it is a phone number, then you can send it to another route, right? So this is one option. The other option is, if you don't want to use event bridge, you can directly send API gateway, push those messages into the SQS as well. In this case, you might need multiple endpoints, something to keep in mind. One endpoint which might put a message into an SMS SQS queue or other one. But in this, where it helps is you're totally getting rid of the Lambda function, which was previously only doing the routing based upon the logic. So API gateway can instantly scale and handle and do that by using the direct service integration. So queuing is definitely a well-known or a well-established strategy. The database queuing is the second, is another technique that you can also use. So talking about databases, like how do you actually prepare your database for hyperscaling? So let's look at the Amazon Aurora in our architecture. So for those, if you have not worked with Amazon Aurora, it's a relational database, and the provisioned mode of Amazon Aurora offers a cluster of nodes. So you would get one single primary node, and then you can have up to like 15 read replica nodes. Compared to like the RDS, MySQL, or Postgres, which comes on with its own EBS volume, what Amazon Aurora does is it uses the shared distributed storage volume. So these reader-writer nodes can interact with this particular shared storage, and then can scale up and down, right, at literally like very low latency lag, replication lag. And then you would also have the reader-writer endpoint as well as a reader node for your application to configure and instrument. Now, one of the challenges or the problem that you run at scale, especially when you're using Lambdas with something like Amazon Aurora, is a connection management, right? So every time you make, you have to keep the connection, you have to establish that connection, keep it open, make sure that it is handled outside the handler code to ensure that it is reusable over the context, right? Now, what happens in a failure scenario where your primary node fails over to one of the read replicas, then you might have to like handle that part. Also, the connection pooling becomes a challenge. So one of the ways to solve that is using something called as RDS proxy, which is a fully managed, highly available database proxy solution. Now, the way how this works is your Lambda function will talk to your RDS proxy, which manages a pool of connections, and it'll ensure that even during the failure scenarios, it will handle all of those things seamlessly for you, so that you don't have the overhead of managing and maintaining that. The second problem that the RDS proxy handles is also these queries which are made to those reader nodes, they are DNS based queries. Now, there is a possibility that when you have multiple of these Lambda execution environments start spinning up at scale and then starts querying this DNS, it can get pinned to a specific reader node, right? So it becomes quite less efficient. So RDS proxy solves that problem by being a network level load balancer as well. And then you get the the other advantage that it integrates seamlessly with secrets manager, so that you don't have to hardcode the database credential. Never do that in production. Here you have an option that it can use the secrets manager, and then with your role that you have configured on your Lambda function, the execution role, you can fine grain and say which particular secrets is allowed or denied. So that's RDS proxy. Let's look at DynamoDB. Now, DynamoDB is a NoSQL database, and it offers two modes on a high level. Like one is a provision mode and the on-demand. Now, provision mode is suitable for use cases where you have a steady workload, where you have a gradual ramp, pretty much like where you know your traffic pattern well in advance. In terms of the pricing, it basically follows based on the read capacity units that you need, or the write capacity units that you would need on that particular table. Whereas on the on-demand side of things, this is for cases where you would probably have an unpredictable traffic, like you don't know what your traffic pattern might look like. It's also suitable for cases where you might have workload that is pretty much idle for most of the time. So you just set it up and forget about, you don't have to configure your WC or WCUs or RCUs. Now, the way how on-demand table scales, right? In general, how the DynamoDB scales is by adding partitions. So this is where it becomes quite important that you kind of know your primary key, so that it partitions properly on the key space, right? Now, when it comes to on-demand DynamoDB table, every time there is a peak, right? It's able to scale twice your previous peak. So when there is new peak that comes in, your traffic, the table on the back end will automatically start adding more partitions and start scaling up and up, right? So why is this important in this context, right? So if you know your traffic well in advance, for your hyperscale event that is going to come up, you can actually do a load test of your full capacity on your DynamoDB, test your application, so that your DynamoDB table is scaled out with all of these partitions being added. And then do nothing, and then wait for the event to happen, right? Then on your day of the event, your DynamoDB is ready to go with all the partitions scaled up. Now keep in mind, once all these partitions are scaled, we don't scale these down, right? So this is an advantage in this case. Now, once your event is all done, from a cost standpoint, what you can do is change that on demand to provision concurrency. So now by looking at the metrics, you would already know what is the WCU that you need or the RCUs that has been consumed, and then you can configure it. So that works very well from a long-term standpoint. So we looked at the DynamoDB. Another important strategy that will also help for an hyperscale is caching, right? Caching at multiple layers. So what are some of the things that we can do in this architecture to improve that or add to that? So first, we have the static component here, which is your front-end application, which is served through the CloudFront distribution. Now, CloudFront itself, you have several options where you can configure the type of cache behaviors for your application, so that these things are cached close to your users. Now, caching is not just for static content, right? You can also have some options where you can cache certain dynamic components as well. So maybe some metadata that doesn't change very frequently. So in this case, let's start from the database. So what are some of the options that you have here, right? So initially, if you look at this architecture again, so all the Lambda functions are invoked synchronously. Some of these queries are just doing a lookups on the database. Maybe there are some metadata that rarely changes. So there are some opportunities here to change it. So from the caching standpoint, you have Amazon Elastic Cache, which comes with Redis or Memcache compatible instances that you can configure. So when the Lambda function is making a query to your relational database, it can first check if the data is already there in Elastic Cache. If it is not there, then it will go and fetch it from the Aurora database and then add it to the cache, so that the next request that comes in will be pulled from the cache. Similarly, on the DynamoDB side, you have the DAX, which is the DynamoDB accelerator, where pretty much from an SDK standpoint or from an API standpoint, everything remains changed. So you don't have to make any code changes there. All you have to do is change the endpoint, and then you're good to go. So even in this case, if you're doing some read operations, it will be fetched from the cache, but any writes will go directly into the DynamoDB table. So that's about database caching, or the caching on the database side of things. But how do you apply these to a multi-tiered kind of cache, right? So we already looked at the DAX and the Elastic Cache. Talking about Lambda, there are some few options that you can also cache certain things in the local Lambda execution as well. So by default, you get something called as a temp space. So again, that's configurable. You can configure anywhere from 512 all the way to 10 MB, I think. And then you can make use of these reuse cache. Keep in mind that temp space that you have on the Lambda functions, so they might not exist or they might not exist in the next execution duration. So that's something that to keep in mind. API Gateway also has a feature where you can configure caching, which is an option that you can configure to cache your GET endpoints. And then we have the CloudFront distribution here, which will act as your the kind of CDN layer, with the API Gateway as your origin. So any request that comes through CloudFront, if you have to fetch something, if it's not there on the cache on CloudFront, then it goes to the API Gateway. Now, how does it work behind the scene, right? So when a request comes in from a user, which is predominantly the DNS queries that it would make, based on where the user is located, the CloudFront will route that request to the nearest edge locations. And in AWS, we have like the hundreds of these edge locations. So it will be routed to the nearest edge location first. And if that object is found in that edge location, it will be served from there. In case if it is not found, then it actually goes into the regional edge cache, right? And again, if these objects are there, it will be served from the edge cache. If it is not there, then it will go to the API Gateway, which is configured as origin. Now, there's another feature that's available in CloudFront, which probably is not very well known, called as the CloudFront Origin Shield, right? Which you can optionally enable it as well. So where this will be useful is all of these requests which are coming from multiple regional edge caches, rather than going it directly to the API Gateway, you add another layer of caching here, which still is within the CloudFront network, and you can get better cache hit ratios, better network, because it still is in the backbone of this CloudFront distribution. So less load in case you're not stressing the origin as much. So this is how you can do the multi-tiering caching. Now, the other challenge with enabling caching at multiple layers is like what happens if the content becomes stale, right? Then there is a challenge of invalidation and things like that. So configuring that TTL is something plays a very important role. So keep that in mind. All right. So far you have seen some of the architectural changes. Now we're going to talk a little bit about like how do you estimate what your service quota means. Like before you do your load testing, like how do you work out like what are those numbers which looks like? And this is where I've seen like a lot of customers struggle a bit or find it a bit difficult to kind of follow that practice or estimating the quota needs. So the first thing that you may want to do is if you have an upcoming event, maybe you want to see what your user journey will look like, right? So you start mapping your user flow. Maybe for an e-commerce application, you have 5 search functionalities and maybe 1 checkout process. So that will be like kind of your user flow. So that will give you a starting point, and based on that you can also work out your Lambda concurrency or estimate your Lambda concurrency. So using the formula that we have seen before, right? So now once you have got this concurrencies or these 2 things, you just sum it up and aggregate the total. So let me show you an example of how you can calculate this thing. So let's say you have an upcoming event of a sale event which is coming to give a few things to users freely. Right, so the marketing team is advising that you are going to have like 10,000 users in the first 3 minutes. So if you directly take that divided by 3, so that comes to 3,300 users per minute roughly. And if you want to calculate that further to a request per second divided by 60, and you would get that number, right? So 60 requests per second. But in a free giveaway kind of an event, you will always have users who will be like constantly refreshing the page, right? So I would double that capacity and say that for my load testing, I would probably use something like 120 requests per second as a safe thing to test it out. So with 120 requests per second, let's work out to see what does my Lambda concurrency needs looks like, right? Now we have seen some of the techniques where to see what are the things that you can do, cold start perspective. What are the things that you can actually minimize to do that? What does your warm start duration looks like? So there are metrics available to kind of work that out. Document all of those things somewhere. Your average duration, your P99th percentile to tell you what is the 99th percentile of your function duration and execution, right? Why is that important? Because that will kind of help you to work out during the peak when you get a sudden burst of all of those requests, right? When you don't have any Lambda concurrent execution environment at all, like what does your concurrency needs look like? And then once you have that all steady state up and running, or your concurrency is all up and running, like what does a non-peak concurrency looks like? So here is an example with 120 requests per second on the API, and your function duration is taking 500 milliseconds. Roughly I need about 60 concurrent executions. And then during my non-peak hour, which has a spread of like 20 requests over the period of like maybe a second, with 100 milliseconds, it takes, I roughly need 2 concurrencies, right? So I've got this number. Now if I sum it up, all of those things, and then match it to the API gateway quota that we have seen initially, as well as the Lambda burst, as well as the concurrency, to see which of those I need to open up a service ticket, or I need to open up a case to up my limits, right? So in this case, talking about the API gateway, it comes to about roughly 9,000 as your burst, right? But I know that in my account, I can go up to 10,000 requests per second. So in this case, I'm okay. But if that number was higher than that, perhaps I would have requested a limit increase. Now for the Lambda, the anticipated concurrency comes to about 2,000. Now you know that by default, it comes with 1,000, right? So in this case, I would definitely open up a support case to get that limit increased. So this is an approach just to show you how you can go about estimating your concurrencies, or to work out to see what is the request per second and how can you document this in order to do your next step, which is load testing. So I can't emphasize like how important load tests can be for most of your events, like where you do the hyperscaling, right? So you can use any framework that that you want to do a load testing, right? And generally, when you do a load testing, If you have the request coming in through the cloud front and going all the way, that's probably the best way to do that. And some of the toolings, some of the load testing tooling, keep in mind that because this request might be generating from a certain instances or certain specific location, it might be hitting the same pop location. So it doesn't give you that real like user-like experience. In that case, you might want to disable your CloudFront and go directly to the backend, right? And then see the behavior to see, do a full-fledged test with the CloudFront, without the CloudFront, and if you have caching, do a test with the caching and without the caching. So that way you can see that when you have those cache hits or cache misses, what is the behavior on your backend system. So you could get the overall picture. Just talking about the observability, like how do you get the overall picture? So you can use any of the tooling system that you have, which will probably give you that observability factor. In AWS, if you're using, you can use a service like X-Ray, which kind of gives you that service node saying, here is a request that first hit this particular function, and then it has gone to multiple of these paths. And with the color coding, you can easily find out, where the function has broken, which particular service is not performing as expected, and then you can start deep diving into it and then investigating it. So the X-Ray SDK further, not just enabling it, but you can also instrument it to see what exactly is happening inside your Lambda function executions. So these are called as segments, or the more information that you can add to exactly see which part of your application might be contributing to the slowness. All right. Some of the important metrics that comes with API Gateway is like some of these CloudWatch metrics might be handy to monitor during your load test. Something like 4xxx or 5xx errors, your latency and the integration latency. So the latency and the difference between these two things. So latency will, from the time the API Gateway has handled the request to your backend, like which is Lambda, it will kind of measure the overall round trip all the way the response has come back to API Gateway. Whereas integration latency will be only from the point it has handed off the request to the backend up to the point the request has come back to that backend, right? So you will get that difference. And you can plot and configure the alarms accordingly. Same way with Lambda. So there are some key metrics that you would definitely need to monitor: errors, throttles, concurrent executions as well, right? And in terms of the concurrencies, also you would get to see what is your account concurrency. When you have a sudden burst, you might consume all the concurrency and starve, run into a situation where it might starve the other Lambda functions. So it's highly recommended to monitor the concurrencies as well. All of these things, sorry, don't mind if I'll be here to take the questions later on. Yeah. I'll just want to finish off all of these things. So all of these things will be very overwhelming when you're doing it for the first time. So there is a new feature that we launched called as CloudWatch Alarm Recommendations. So what it will tell you is, based on all of these factors, it will tell you what are some of the key things or the key alarms that you can configure on your Lambda function. So I would definitely recommend having a look at this particular feature. Certain other techniques that you can do is error handling and retry. So this is also very important. So Lambda, you might have already know that it has a maximum duration of 15 minutes, right? You don't have to keep it to the default, which is the 15 minutes, if your function is only taking less than a second. So look at your CloudWatch metrics, look at the metrics, and then configure the P99 percentile to be an appropriate timeout here. Retry and back off, right? This is quite important, especially when you are retrying the request. You don't want everything to be retried at the same time, because that will cause a stampede effect. So the technique that you would follow in this case is exponential, where you would give a random way of like exponentially retrying, so that all the requests doesn't retry at the exact same time. Implement idempotency. Basically, idempotency, what it means is, if a request has been retried multiple times within a very short duration, can my application still be working as expected, right? Something like payment transactions, right? You don't want the payment transactions to happen twice in case if the first one did not go through. So this again is another 1 hour of talk. So I'm going to leave the link in here for your reference. So one of the things that during this COVID-19 application, several customers who were launching these apps were requesting for this particular feature is the virtual waiting room, right? Where instead of customers retrying and hitting that button over and over and again, what if you would you'd be able to redirect the customers to a page which will tell them, what position they are waiting in. So that way, kind of, they don't hit that refresh button as often. So we have actually open sourced a solution which is available on our GitHub repository. It has been tested for nearly about 100K users, coming in at about 1,000 requests per second. This is an open source solution where you can take the base architecture and then you can add or customize that according to your needs. All right, so we've covered most of the things. So let's summarize this, and I'm going to be here if you have any questions on any of those topics. So please find me, and then we can talk about it. So going back to our initial architecture, so this is what our architecture was, right? So the first practice was to understand the serverless compute scalability. Like, this is talking about the API gateway limits as well as your Lambda limits. So we talked about like 10,000 has your base requests, and then on the Lambda side, it has a default of 1,000 concurrencies, and then you can, all of these numbers are soft limits which you can raise it. Next is optimizing your Lambda functions. Optimizing your Lambda functions for cold starts. Don't load the libraries that you don't need. Try to see other techniques like minifying or reducing your package size to make the cold starts optimized. Right size your Lambda functions by using a tool, something like Lambda power tuning, right? The next is decoupling, or try to see where in your architecture you can implement asynchronicity. So in this case, we had an opportunity to kind of move away from the messaging services by adding a queue, and then on top of it, you add reserved concurrency so that you don't overwhelm your downstream systems further. Prepare your database for hyperscaling. So we looked at the options of using RDS proxy for your connections pooling, as well as on the DynamoDB side, you can load your, do a kind of a load test on your full capacity so that the tables are fully partitioned before your event comes in. Then you looked at the caching option. So you can use Elastic Cache, DynamoDB accelerator here to cache some of those frequently accessed requests. You also have caching options available at API gateway as well as on the cloud front. And when you are in doubt, always make sure that you provision for peak, right? That's a key takeaway in terms of like how do you go about approaching that, the number that you need for your load testing. So we've seen a kind of an approach or which would work and tell you like what are those numbers that you would need. Perform an end-to-end testing. Again, keep in mind when you have caching layer, make sure that you have kind of a load testing without the cache and with the cache, and then leverage tools like observability to get the full picture of what things are happening and where the full performance. The best practice 8, we didn't talk about this, so I'll cover it up very quickly. So API gateway also has an option where you can throttle requests at the API gateway using the rate limiting factor. So this is kind of useful where if you have like multiple clients and one of the client might accidentally use all of your limits and then starve the other resources from execution. Right? In that case, you can limit those clients specifically by making use of usage plans and the key associated with that, so that that client doesn't act accidentally or doesn't run into this kind of a DDoS kind of a situation. And then you can also optionally use a virtual waiting room solution where you can redirect the user to another page where they would see what position they are in, and then they can access the application once they are let in. So we started with the baseline architecture, and then this is what the full-fledged application looks like, which will meet your hyperscaling requirements to a certain extent. If you want to learn more, there is a page that I can recommend to have a look called as Serverless Land. There's a QR code available which will take you directly to this. What this includes is all the resources from our reInvent, the talks, the best practices, the guides, and probably has like unlimited number of resources that will help you in your serverless journey. One of the other things that this particular page also has is something called as patterns. So if you're starting new and you want to have like an API gateway, Lambda, and a DynamoDB, and you are using an infrastructure as code, maybe Terraform, maybe CloudFormation, maybe SAM, the patterns can give you a quick start or a quick guide to get started by a single click. So just have a look at the patterns page as well. There's another resource called as Amazon Builders Library. I would highly recommend taking a look. So all of those articles that are published here are published by our senior principal engineers, right? These are like VP levels at Amazon. And you can see some of the techniques, and these are sort of white papers in which outlines or describes how they have built the system in Amazon. And one of the nice things about this is this is not specific to a technology. This is not specifically talking about AWS as a service, but in principles in general. So you can pretty much take these principles and apply it to any system that you would work. So something like dependency isolations, managing your failures, configuring or preparing your architecture for resiliency and reliability and things like that. With that, thank you so much. And as a data-driven company at AWS, we highly value the feedback that you would give. And if you can scan this code and give a quick feedback about how the session was, whether anything new that you want to have a look, would really appreciate it. In case if you want to connect with me after the session, there's also my Twitter here. So feel free to reach out, post this. I'm also going to be available on Thursday here in case if you find me, if you want to ask any other questions. So thank you so much.